Invite our next speakers of the first session.
Yeah, thanks, Mohit. Good morning, good evening to all of you on the last day of our conference. And I'm very pleased that our first speaker today is our good friend, Professor Benjamin Kane. He's from University of Hong Kong. And he's associated with this ICCGNFRT from its inception. And he's very kind. Every year, whenever we request him, he's always there. So he works in analytic number theory, in algebraic number theory, in quadratic forms, partition theory, and L functions, elliptic curves, modular forms. So it's everywhere Ben is there. And he's a multifaceted person in mathematics. And one of the most important thing which I want to point out to, we have a large section of young students that Ben guides plenty of, if you go to his webpage, the summer interns, this undergraduates. And if you can see a long list of students from all over, especially from developing countries. And Ben is very kind, and he spends among his teaching and everything, he spends a lot of time with them. And so it's real pleasure for us, Ben, that you are with us. And today, the title of his talk is Moments of Class Numbers and Distributions of Traces of Frobenius in Arithmetic Progression. Professor Benjamin Kane.
Okay, thanks for the nice introduction. So let me say that if anyone has any questions in Zoom, you can go ahead and just type a message right into chat. I have the chat open on the side so I can read it as you speak. As you type it, and I'll just try to answer any questions that come up. So if there's anything that's unclear, go ahead and just ask whenever you feel like it. I don't know if Michel is here, but I want to say happy birthday to him. And yeah, hopefully we'll again be able to see each other in person sometime soon, maybe at the next one of these. You are here. Okay, great. So he says in the chat he's here indeed. Great. So this talk is in some sense partially a continuation of Katrin-Bringmann's talk. It's related to Ken Ono's talk in a certain sense, although we go in a different direction than Ken and Neelam Saika and Ken's student Saad. We go in a slightly different direction, but we're looking at some related questions in a certain sense. So this is joint work with Katrin and Sudhir Pujahari, who some of you might have known from when he was a postdoc well, at another university, but also in India. So some of you may know him. So we're going to start out with an elliptic curve. So when I think of an elliptic curve, I'm not extremely geometric. So I just think of it as solutions to the following equation. So we have a polynomial, f of x, which is cubic, and we're looking at solutions to the equation y squared equals f of x. Now, technically, we look at this projectively. So it's y squared times z, and then f of x comma z, and z is chosen to the power so that it's always homogeneous of degree 3, but these are some technicalities. In many cases, most of the time, we can write it in Weierstrass form. As long as the field characteristic is not 2 or 3, we can do this. And let's say we have x cubed plus alpha x plus beta is our cubic polynomial. So there's some kind of equivalence relation, and these are equivalent in some way. And everyone is equivalent to one of these in Weierstrass form. And I look at the solutions maybe over some ring that generally will contain the integers, or that, for instance, we could take the integers modulo p by taking the reduction modulo a prime. So you can also think of solutions where x and y are now considered to be modulo a prime. So you can take this over many different choices of rings. And for example, if you take the real numbers, you take the equation y squared equals x cubed minus x, then I'm looking at the solutions like 0, 0, 1, 0, 2 square root of 6, 2 minus square root of 6, and so on and so forth. So this will give you some kind of curve. Okay. There's a group law. So this is not particularly too important for what we're doing, but nevertheless, I'd like to just describe what it is if you look at the real numbers. So if you take a line between 2 points, it actually hits the curve at a third point. And essentially, this is because of the fact that the solutions to this equation. So if we look at a line, y equals mx plus b, that defines that y can be now replaced with mx plus b, because we want simultaneous solutions to the elliptic curve and the line. But that gives us a cubic equation to something equaling a cubic equaling 0, because this y squared will not cancel the cubic part over here, assuming that the coefficient in front of x cubed is not 0. So then the third solution, if 2 of the solutions are in the real numbers, the third solution must also be, right? Because if there's a complex solution, there must be a pair of complex solutions by taking the conjugate. So if there are 2 solutions, there must be a third. And then that third one hits the curve somewhere. So in this example, this is the third point that it hits. And the addition between the 2 points we define to be the flipped version of that over the x-axis. Okay, so this is what you get in the real numbers. There's a group law in general. You might ask what the identity is, and the identity is what we call the point at infinity. So like I said before, we're actually looking at this projectively. And the point at infinity is when you take x over y, and you take 1 over 0. That's sort of infinity in some sense. And if you put this in with a z, there's a way to make this make sense. And so the point at infinity, we imagine it as being every vertical line hits the point at infinity, because the vertical line indeed does not have a third solution. If you look at what that means, because that's x equals something, and then the y's can take any possible value. Now, if we take R to be a finite field, then the number of solutions is finite, because we only have a finite set. We have a finite choice of x, we have p to the r choices of x, and p to the r choices of y, plus that 1 point in infinity, and we can count the number of solutions. And if you do that, if you include the point in infinity, you expect to have about p to the r plus 1 solutions overall. So this is kind of the expected value. If you've seen any probability theory, this is the expected value. So it might be very natural to ask, if you have the expected value, how far off am I from the expected value for the actual value, right? So you have kind of an average. The expected value is sort of the average value. If I go across all of the curves, I sort of expect to have this much. And something called the trace of Frobenius, I won't go into the details of what this is, but it's the map that takes a point to the pth power. So this is the same prime coming from our field. Then it turns out that if you take the trace of this, so you can think of the action of this map as a matrix sending some point to another point. And if you do that, if you take the action, you can take the trace, and that's what this is. But from our perspective, the point is that it's the average value minus the actual number of points. And what Hasse proved is that the absolute value of this, so the kind of the amount that you're from the average is in some bound. It's in the twice the square root of the size of the field. It's somewhat natural to normalize that you're within that range. So think of like a normal distribution, right? The normal distribution, you take the average, and if you take the distance from the average and you normalize, then a certain percentage of them will be within this distance, and a certain will be within this distance, and so on and so forth, right? So this is sort of the normalization that makes sense. You normalize so that sort of everything is at most within distance 1 of the average. Okay, so that means that we get a number that's always between -1 and 1. And one of the things that's very nice about that is that this is independent of P and R. This number is always between -1 and 1. And we can now ask, what is the value? How many times do we get a half? How many times do we get a third? How many times do we get between a third and a half? Or between -1/3 and 1/3? So we can ask these kinds of questions now because we get something that's independent of P. The original question, if we ask the similar question here, we'd have to scale it. And so this is sort of a natural scaling to ask questions like this. And so with that in mind, we'd like to ask the question, so for every, as I move something, varying, say, the prime, or varying the elliptic curve, or something like this, as I vary things, I can look at the distribution of where the x sub e's land, right? So I can put them all, I take a bunch of these curves with a bunch of these primes, and I put them all down and I see what the distribution looks like. How many do I have that's at a half? How many do I have that's a third? How much do I have that's between the two? What's the probability that I'm between here and here? So this was described by Kane. He explained this. If you fix an elliptic curve and you vary the prime, then you can ask the question for any a and b, as x goes to infinity, consider all the primes for which the normalized trace of Frobenius is between a and b. So you take all the primes up to some point x, and you ask the question, what is the probability that, what is the probability that I'm between a and b? What's the probability that I'm between a and b? And that's what this number is here. And so the conjecture of Sato and Tate, which has now been proven, says that we should, just a moment, sorry. Sorry about that. So this probability of from the Sato-Tate conjecture says that if we take this probability and we take x to infinity, that the probability converges to an integral. So the probability that you're between a and b converges to the integral from a to b of some kind of natural measure. Okay, so we have a discrete measure, right? We're taking the probability that you're between a and b of all the primes up to x, and this should converge to this natural integral. Now, this conjecture was very hard. It involves a large number of things, and we're not going in this direction. Just as Kane said, we're not. He didn't go in that direction either. So this involved work of Cloisel, Harris, a large number of authors. They proved this conjecture, but this is really involves a lot of algebraic geometry and representation theory, and proving that certain modularity exists for symmetric powers in some sense. So this is a hard conjecture. So this is not the direction that we're going to go in. Instead, we're going to look at a slightly different distribution. So we're going to vary the way that we're taking the probability. So we're going to fix the prime power first. So we're going to fix the field. And what we're going to do is we're going to look at all the elliptic curves over that field, or some subset of them. And now we can take a probability of, so this was exactly what was looked at by Birch. What he did was he said, take all of these elliptic curves in the Weierstrass form and look at the probability that the normalized trace is between A and B. And how many of them are there? Well, there's this should be sorry, this would be 1 over p to the 2r, because that's the number of alpha and beta here. So for r equals 1, it would be 1 over p squared, but in general, it should be 1 over p to the 2r. And then count the number of pairs alpha beta for which the elliptic curve has this normalized trace between a and b, and you'll get the probability that essentially a random elliptic curve over this finite field has the given, it has the normalized trace between a and b. And Birch, what he proved is that indeed this probability also converges to the exact same integral that the Sato-Tate conjecture claimed. This was well before the Sato-Tate conjecture was proven. So in some sense, what he proved is that the Sato-Tate conjecture is true on average in some sense. Although we're varying in a different way. We vary first, see, our probability is defined very differently. We're not dividing by the number of primes. We're dividing by the number of elliptic curves of that prime. Although in some sense, some of these elliptic curves are the same, depending on how you define the same. If they have different Weierstrass equations, but they have some kind of equivalence. We're going to describe that in just a moment. Okay, so there are two different equivalence relations. One of them is called isogeny, and one of them is called isomorphism. The isogeny classes are determined by the number of points. So our normalized trace is equivalent to the isogeny class. And in each isogeny class, we might have many different isomorphism classes. So for example, these E alpha betas that were described here, beginning, these E alpha betas may actually have some multiples of them might be in the same equivalence class or the same isogeny class. So we're saying that we're breaking them up into groups that are the same or different. And so what we're going to do is we're going to take a subset of elliptic curves over the finite field, not necessarily the whole subset. And so the whole subset is equivalent to what Birch did. And we're going to take this weighted probability. And this weighting turns out to be natural, where you divide by the size of the automorphism group. And the reason that we're doing this is essentially if you look at how many of the elliptic curves are the same under isomorphism in Birch's example, then actually it's the same. This is the same probability that Birch was looking at. This is actually the same normalization, because although he's dividing by 1 over p squared, he's actually in this counting, some of them are counted multiple times. And so they get weighted differently if you count them by isomorphism class. So this weighting is actually natural. And so that's what we're describing here. So we're going to look at from the perspective of isomorphism classes. So we need this sort of weighted probability distribution. We take all of the elliptic curves in our subset of the isomorphism classes, and we count how many of them have the normalized trace between A and B, and then we divide by the weighting so that the probability of, if I put A and B minus 1 and 1, the probability will be 1, right? So this is kind of a weighted probability. And the case that we're going to be interested in for this talk is the following. Consider the set of isomorphism classes for which the trace is congruent to little m mod capital M. So we could have it be 5 mod 7 or 1 mod 101 or something like this. So we fix a capital M and we take all of the elliptic curves whose trace is in a certain congruence class. And then we can ask about the distribution in the same way that Birch did. So we go across, for every prime, we go across all the elements of this, right? So the field is fixed. We look at all the elliptic curves of this type. And we ask what the distribution looks like as I divide by the number of isomorphism classes. And what we prove is that indeed we get the same, the same as Birch did. So what does this say? So here I have the probability that we're between A and B for this subset is the same distribution as the distribution of all of them. So think of this as a conditional probability. So the conditional probability is the same as the probability in the original class. Does anyone know what that's called? We'll call that independence, right? So the probability, the weighted probability in this case, that the elliptic curve is in this has the trace in this congruence class is independent of the Sato-Tate distribution. So the two things are independent. That's what we're really proving. We're proving that the congruence relation for the traces and the normalized traces lying in some region are independent of each other. Now, so for how do we go about this? The basic idea is that any kind of reasonable distribution is actually determined by the moments. So here we have the weighted moments. So we take the x sub e to the kappa power, where kappa is some integer bigger than or equal to 0. And you can think of it like this. The moments, so if the x sub e is very small and we take it to a large power, it gets smaller and smaller. But if it's very big, then it doesn't get small at the same rate. So it turns out that by some probabilistic methods, you can prove that if you can figure out all of the moments, that completely determines the original distribution. So it tells you the probability overall. And so we study these, and we show that as the prime goes to infinity, this converges to the same as the moment of the integral. And what is important is that, see here we go from A to B. For the moments, we just have to go from -1 to 1. But then we have to take the powers of this. We have to take powers of x here, because that's what sort of is varying here, right? We're taking x to some power. And so we have to take x to some power inside the integral. And so we have to compute and compare the moments in the integral and the moments in the discrete distribution that we're looking at. And we have to show that one converges to the other. As the prime goes to infinity, it should converge to the other distribution. That's equivalent to what we're claiming. This is the same method used by Birch, so this is nothing new. This is an old method, and it was used before Birch to prove that certain distributions are the same. So instead of taking this, we take the trace itself to the kappath power. But remember that this is just the trace divided by 2p to the square root of p to the r. So there's just a p power and a 2 power that vary between these two definitions. So computing one and the other is equivalent. Okay, so that's the relationship between the two. And what we prove is, in other words, to be able to understand these moments, we prove that if we take this ratio of the kappath moment to the 0th moment times some 2 power and some p power, which is, sorry, this should be, I think I want p to the r here and p to the r here. I think so, yeah. So I think I should have p to the r here and p to the r kappa over 2 there. And then what we get is, we get that this is the Catalan number divided by 2 to the 2k if kappa is even, and it's 0 plus some error term that goes to 0 as p goes to infinity if kappa is odd. And this sort of makes sense because we sort of know from Sato-Tate conjecture, we sort of know that these normalized traces are sort of equally often positive and negative. So as we take an odd, if we take an odd moment, then you sort of expect things to cancel. And in Birch's case, they just cancel directly. In Birch's case, there's actually a bijection between those that have a positive value and a negative value, and they cancel. But of course, the congruence condition may not be satisfied when you go from plus to minus. So then they don't directly cancel in our case. So we have to actually do something here to prove that this really does cancel. But it does what you expect it to do. You would expect cancellation if you take a bunch of pluses and minuses. You expect some cancellation at least. And you see as the even moments won't have any cancellation because you're taking a negative number to an even power. So the alternation in sign disappears. And we compare this with what happens for the Sato-Tate distribution. So we're taking the integral of x to the kappa of mu of x dx. So as I said, we amplify it by this x to the kappa. That's the moment for the integral. So you can think of an integral as a sum in some sense, right? You can write it as a sum, as a limit of a sum. And you get this integral can be computed as ck divided by 2 to the 2k if kappa is even and equal to 2k and 0 otherwise. So these exactly match in the limit. And that's how you prove the previous claim. So far, I haven't mentioned class numbers at all. So you might wonder where those come in. So far, we just talked about elliptic curves. Well, Schoof, again, this was mentioned in Canona's talk, showed, so using Deuring's results and making them explicit, he showed that for most of the T, the number of classes in the isogeny class, so the number of classes that have the same trace, T, for some fixed T, is a class number of an imaginary quadratic field. So this is the Hurwitz class number. And what you do is you take our moments and you rewrite it by just counting these things that have that T. You get this, which is just the same thing, plus some error term, essentially. So there's some that don't exactly match, and you have to do something in those cases. So you kind of get this formula, and it moves the problem. So using this result of Schoof, it moves the problem to studying these moments of class numbers. And so this is where we look now at class numbers to be able to do something about elliptic curves. This, as I said, this is the Hurwitz class number, which sort of counts the imaginary quadratic fields or the imaginary quadratic orders of a certain type. From the point of view of binary quadratic forms, I'll describe it in the next slide. And you can show that this error term is actually an error term. So I won't really discuss that. This is fairly explicit. You can bound it using some straightforward techniques. And now we have to study these moments. So the Hurwitz class numbers from the point of view of binary quadratic forms just counts the pairs A, B, C of discriminant D for D less than 0. So different people use different notation. Here I'm using H of absolute value of D. Some people write H of D. So this is the number of binary quadratic forms of discriminant D up to isomorphism, but I don't necessarily assume that they are primitive. So A and B and C can have a non-trivial GCD. And I weight them by a half if they're equivalent to x squared plus y squared times a constant. And I weight them by a third if they're equivalent to x squared plus xy plus y squared times a constant. So these two special binary quadratic forms that only show up in when the discriminant is minus 4f squared or minus 3f squared, I give a slightly different weighting. Again, this is natural in a certain sense. So the way that we're going to study these things is we're going to view these class number moments as coefficients of automorphic forms or modular forms in some setting. So we want to build generating functions that have these as their coefficients. And that's how we're going to proceed forward. We start out with a theta function, which is just exactly the moment showing up. So this T satisfying the same congruence conditions. We take T to the kappa power. So we're trying to take the kappath moment, Q to the T squared. And then we take the generating function for the class numbers, and we take their product. And now if I multiply these together, and I write n equals d squared plus t squared, then rearranging, I get this formula, and you see that the coefficient of q to the n is just this class number moment, the kappa class number moment, and we want the n to be 4n. So we look at the 4nth coefficient of this. So now if we can study this product, we can study the problem we're interested in. So to study the product, we want to study the individual pieces. Ken Ono described how to do this in some detail. I'm going to cheat a little bit. I'm going to take a sort of simpler path, although the method that we use is actually the same as the one that Ken did. So I'm going to describe this in a slightly simpler way, just to make it perhaps easier to follow what's going on. So we want to study the modular properties of this product. Now this theta is almost a modular form. If I put kappa is 0, it is a modular form of weight 1/2 on some group. And if I put kappa equals 1, it's also a modular form of weight 3/2 on some group. So as Ken described it, he started with these, and then he used something called Rankin-Cohen brackets to go up in weight. And so he was really dealing with modular forms. But you can also simply take these and take derivatives of them. If kappa is even, I take derivatives of the theta 0. And if kappa is odd, I take derivatives of the theta 1. And if I take k derivatives, I get the 2kth moment here. And here I get the 2k plus first moment. I mean, the theta function corresponding to our 2k plus first moment in the previous slide. But derivatives of modular forms are what we call quasi-modular forms. And quasi-modular forms miss being modular forms by only a little bit in some sense. We have some way to sort of fix them to make them into some kind of modular object. So what is a modular form? I know some of you are familiar with them. Some of them may not be. So the primary property that we want for a modular form is modularity. So it has a certain symmetry that cz plus d to the minus k times f of gamma z is f. For some subgroup of SL2z, it's holomorphic on the upper half plane, and it's bounded towards the cusp. So if you go radially down towards h over k, it should be bounded in some way, or at least the growth doesn't grow too fast, just polynomial growth we allow. We allow half integral weight. So for this, we have a kind of multiplier system. Without the multiplier system, these don't exist. They can't simultaneously, because of the square root not being, because of the branch cut of the square root, it's impossible to have it just be cz plus d to the minus k when k is a half integer. So we have this extra factor that sort of fixes that. And we have, this always has absolute value 1 when we deal with these. Again, we assume holomorphicity and bounded growth towards the cusps. So what are these quasi-modular forms? Well, I assume the same kind of property, but now I change something. I change it so it's no longer necessarily holomorphic. I take a polynomial in the inverse of the imaginary part. So z is x plus iy here. I take a polynomial in the imaginary part with coefficients that are holomorphic. And this thing is what's going to replace holomorphicity. So it's almost holomorphic, which is why this name is given. And some people call it nearly holomorphic, depending on the literature. And the constant term, the f0, is what we call a quasi-modular form. So these derivatives of modular forms are proven to be quasi-modular forms. So these derivatives, every time you take a derivative, the L goes up by 1 is what happens. So these derivatives of the theta function are of this type. They are the holomorphic part. You know, there's no power of y here, so they're sort of the holomorphic part of an almost holomorphic modular form. So they're not too far from being modular forms in some sense. Now, Zagier looked at the class number generating function, these Hurwitz class numbers, looked at the generating function, and found that it's almost a modular form as well. And in what way is it almost a modular form? Well, we have to add this non-holomorphic piece, which many years later was proven to be part of a sort of family of objects called harmonic Moss forms. So this H hat is what's called a harmonic Moss form. We don't care too much about the properties of harmonic Moss forms for this talk, but the main important fact that we want is that this transforms like a weight 3/2 modular form. So we have a weight 3/2 modular form that's non-holomorphic times times an almost homomorphic modular form. And if we take the product of those, we'll get some modular object, but we only want some piece of that, right? We want the non-holomorphic, we want the holomorphic piece. We just want this product, which we had to add something. We have to add these other terms for the almost homomorphic modular form, and we have to add these terms for the class number generating function. So we complete both of them, and then we take the product. And this will be a kappa plus tooth non-homomorphic modular form, because when we take the derivatives, the weight goes up by 2 every time. So the weight here will be exactly kappa plus 1/2, and this one has weight 3/2. So when we add them together, we get kappa plus 2. So this is a modular object, but it's not holomorphic. And what we'd like to do is we'd like to understand the holomorphic part of this that comes from not having the hats. So what do we know about non-homomorphic modular forms? What can we learn from these objects? Well, we have, on holomorphic modular forms, we have an inner product that Peterson defined. So if we have F and G, we have the inner product between them. Well, you might ask why this is well defined. So F times G bar, the imaginary part to the kth power, dx dy over y squared, if it satisfies weight k modularity on the same group, and so on and so forth. So the way to think about this is to consider z and z bar as independent variables, right? So if I take the derivative of one with respect to the other, I get 0. That's what the Cauchy-Riemann equations essentially tell us when you define homomorphicity in that way. And the weight kappa 1 or k1 and k2 modularity will define to be anything that satisfies this modular property with some multiplier system. So we have cz plus d to the k1 power, cz bar plus d to the k2 power. And so we allow some part of the modularity comes in the z part, and some part of the modularity comes in the z bar part. And if you do this, because f has weight k modularity, and G bar has weight k modularity in Z bar, then their product has weight k modularity, comma k modularity. So it's weight k, comma k. But the imaginary part has weight -1, comma -1. So if you plug in, make the change of variables, Z goes to AZ plus B over CZ plus D, and rearrange and compute using the fact the determinant is 1, you can actually show that this is a modular object of weight -1, -1. And so when I multiply them together, this becomes invariant, because this is weight k, weight k0, 0k, so kk, minus k, I get 0, 0, that's invariant. And the measure is also invariant, you can prove that, so everything is well defined. Now there's also a question of convergence. We won't worry too much about that. If these are cusp forms, it's fine. But we also want to take not just cusp forms, we want to even plug in non-holomorphic objects. But here's something that's very interesting. It's positive definite on the space of cusp forms. Because if I take this definition, if I take f and g equal to each other, so I take g equals f, then this becomes the absolute value of f squared, and everything is non-negative here. So this is clearly going to be non-negative. The only way we can get a negative value is when things diverge. And indeed, if you try to take an Eisenstein series with itself, the naive integral is divergent. There's an analytic continuation, but then it's not positive definite anymore. So what can we say about a positive definite inner product? Well, a positive definite inner product has an orthonormal basis, and the inner product, if I know the inner product of G with all of the F's or even all of the orthonormal basis elements, if I know this value of this inner product, then that uniquely determines the form. So you can do Gram-Schmidt orthonormalization, for instance. So this inner product kind of gives me what G is. So now I'm going to replace G with a non-holomorphic object. And if I do that, then if this exists, which it won't necessarily, but if I have a modular object for which this always exists, then there's a unique little g that has the same value for the inner product for every f, because that uniquely determines the form. So if I know this value, I can determine a g that has the same value. Now he called this the holomorphic projection. It's sort of the holomorphic piece of capital G. And he computed its Fourier coefficients as some integral. But this integral, then Gross and Zagier took as the definition of the inner product. And they showed that actually, if you take it as an integral, then you can now apply it to things that are not modular. You can apply it to anything essentially that's translation invariant, for which has this kind of formula. And the homomorphic projection preserves now certain things. It preserves modularity because that was the original construction of Sturm. It also is the identity function on holomorphic functions. So if you take a holomorphic function, it does nothing, even if it's not modular. Now we take f hat and we split it into two pieces, a holomorphic piece and a non-holomorphic piece. And we assume that the left-hand side satisfies modularity. And the f is holomorphic, and we apply holomorphic projection to each piece. So the holomorphic projection of f hat is the holomorphic projection of f plus the homomorphic projection of f minus, where f minus is whatever's left over. So we have some modular object, we have a holomorphic piece, and then we have everything left over. And we apply the homomorphic projection to each of the three pieces. But since homomorphic projection is the identity on holomorphic functions and our f was holomorphic, this does nothing to the f. But the good news now is that we can now solve for f. So f is the homomorphic projection of f hat minus the homomorphic projection of the remaining piece, the f minus, the non-homomorphic part. Now, the first term is if f hat is a nice non-homomorphic modular form, it will be a Cuss form, just like Sturm had. If it's a little bit more exotic, so if it allows some growth towards the cusps so that the original integral doesn't actually exist, but some sort of continued version, analytic continued version of it does, then you get a quasi-modular form or some slightly more complicated object. But the point is, the first piece is some modular form of some type. And modular forms we have a lot of control over. We know how to compute their coefficients. We know how to study them. So part of the f we now understand. If we can compute the remaining piece, then we understand f. And that was our original goal. F, in our case, is going to be the product of the class number generating function times this theta function, which was some holomorphic object. So we'll get that as the coefficient of this quasi-modular form minus the coefficient of this holomorphic, this non-holomorphic piece, which we've projected into a holomorphic part of it. And for Mertens, for the kappa even, computed the holomorphic projection of this f minus, and following a similar calculation, Ono, Saike, and Saad computed these for kappa odd. And basically what these give are sums of this type, where they are sums of divisors. And I call them the smaller divisors because d squared is less than n. So d is less than n over d. So you get the smaller of the two divisors whose product is equal to n. And they satisfy some congruence condition in our case. D plus n over d is 2m mod 2 capital M. So sometimes these generating functions are called Mach-Eisenstein series. And they're very similar to the usual Eisenstein series, say for SL2Z, where you take the sum of all divisors instead of the smaller divisor. So it's basically the same type of sum, just a different condition on which divisors I take. Now the kappa equals 0 moment actually gives you the main term. And it turns out that if you rearrange things, it comes by induction to all the higher even powers. So for kappa even, this gives the main term. And then the quasi-modular form that we got essentially has an Eisenstein series part and then a Cuss form part. And the Cuss form part, Deligne has proven that these coefficients are very small. Actually, we don't need as strong as Deligne's result. There are weaker results like those of Hecke, which are good enough for most of our cases to bound smaller than the main term. But nevertheless, this is the best bound you can get. So we use this one because then we have a clear range between the two. Now, these sums of smaller divisors are fairly small compared to the Eisenstein series coefficients, right? The Eisenstein series coefficients are like d to the kappa plus 1. So basically n to the kappa plus 1. And these are like n to the kappa plus 1 over 2, because the divisors are all smaller than the square root of n. And so you get this kind of bound. Each of them is smaller than the square root of n, and then take times the number of divisors at most. So this is sort of small compared to that. And so when you put this all together, you get that the main term comes from this Eisenstein series. And going back, that tells us the coefficient of this product of the holomorphic part. And then that was in turn precisely what we had here. So this now, we're able to show this part, the main term of this part, plus an error term, the error term coming from the cuspidal part. The cuspidal part is sort of, as we know, the cuspidal part goes up and down like crazy. The coefficients are positive and negative, and they're hard to control. Basically, the Sato-Tate conjecture tells us that they're infinitely often near any value that we want. So we can't control the cuspidal part very much, but luckily the cuspidal part is smaller. So that allows us to get a main term and an error term, and then this error term is also smaller. So altogether, we get the main term for this S, which was exactly the moment of the traces. So that gives us the main, that gives us this theorem, which then goes back and gives us the original theorem about the distribution. And that's all that I had for today. I hope that it was interesting, and look forward